what would be the average of all of these values against time that I have here? Now, if I go and look at this graph, I will see that that average is 0. Now, if I can show you why is it 0, I'm going to move over to my camera. And on my camera, I just want to show you the reason for that. So let me just put the paper here underneath my camera. I'm going to shortly switch over to the camera. I'm going to show you that very same graph. I have my graph of potential difference against time. And let's say this was the graph. And I'm only taking it up to that time t. Okay, so let's call it T1. If I look at all the values here, then I will be able to say that the average potential difference will have to be 0 for the time from 0 to T1. Why? Because for every value here, I have a negative value there of the same value. Right? So the moment when that happens, my average will have to be 0. But then if my average is 0, how can all the lights in our homes then function? Or apparatuses in our home function? Because my average potential difference is 0. That will have to mean then that my average current would be 0. And my current will look exactly the same shape. Might not have the same maximum values, but my average current will also be 0. Now, if I look at my bulbs at home, it means that the power, the brightness of that bulbs, which is equal to, and you don't need to know how we get this formula, you will receive it. I mean, it's the average potential difference multiplied by the average current. It means that those things actually will have a 0 value, because I will substitute a 0 and a 0, which is not happening. It is burning with a certain brightness. So I can't work with this average. This average is not what I want to be able to explain the brightness or the power of the bulbs in our homes. So what we then introduced was the root mean square. The root mean square of the potential difference and the root mean square of the current. Now, if I look at those two, I can easily calculate that root mean square. That root mean square is that maximum potential difference divided by the square root of 2. And that formula is given to you. So what does that mean? That means that if I look at that maximum value, Vmax, all right, then that value I just substituted in there divided by the square root of 2. I get a value which we call the root mean square value. And it's a value somewhere in this vicinity there. A little bit lower than the max, because I've divided by the square root of 2. And if I take the root mean square of the current, it's the maximum current divided by the square root of 2. All right? So it will give me, there's my maximum value, it will give me a value which is a little bit lower. But what we find then, if I do this calculation now, where I can say that the power is the potential difference root mean square now, multiplied by the root mean square of the current, which I've calculated through those two formulas. Now I've got an equation which shows me the brightness of that bulb. All right, so we have to go, because of the alternating current where the values is not constant, like in a direct current circuit. In a direct current circuit, this graph will look like this. The potential difference will remain the same. And the corresponding current against time graph, the current will remain constant. You see? So when I multiply those two with one another, it will give me the brightness of that lobe. All right? So I can't use the maximum because the value, the average, the value is not always the maximum, or the average is 0. But when I come up with this root mean square, there I've got a way of calculating the brightness of a bulb which is linked to alternating current. All right, so just be careful. There I've talked about direct current. This part is alternating current. And from here on, Ohm's laws apply, but I always have to first take my max to the root mean square value. Then I can apply my Ohm's laws and everything the same as in normal electricity to get my values that I want to calculate, and that is why I also then can have these or I can have V square over R, but I will use the root mean square values there to calculate the power. But these are given to you. It's on your data sheet. We can now just look at applications of that. So let us go back then again quickly to the slide. Now let us just, for refreshing purposes, look at what is it in this section that we need to know. First of all, we said state the advantages of alternating current over direct current. We will come to that. All right. Then sketch graphs of voltage versus time and current versus time for alternating current circuit. That is what we've looked at just now. Define the term root mean square for alternating current. The root mean square value of the alternating current is the DC potential difference or current, which dissipates the same amount of energy as an alternating current. So that means just that root mean square is a way of having that average which I can associate to direct current. Okay, and we will have the same brightness of bulbs, for instance. And then we've got calculations, solving of problems. So if I looked at the first three bullets, we only still need to look at bullet number 1 and maybe look at examples of solving problems. Then we've through alternating current. Right, so let us go now to the slide where I just want to recap on everything for alternating current. All right, where will we find that alternating current? It will be generated from a generator. So if you look there, I've shown you my generator, and we now know that that generator will have to have split rings. Okay, all right. Now I'm lying, slip rings is associated with that. Right, then I've looked at the graph. All right, so this is an alternating current graph for the potential difference, where the potential difference, depending on which stage of rotation I am, then I will have these different induced potential differences. All right.